Okay, it's my pleasure to announce Konstantin Loginov from Higher School of Economics and Steklov Institute, who will speak about regularity of smooth Fano threefolds.
Okay, thank you for the introduction, and thanks the organizers for the opportunity to be here. Indeed, I will talk about co-regularity of smooth Fano threefolds. This is a joint work with Artem Avilov and Viktor Pozhelkovsky. And we will work over the field of complex numbers. Okay, so let me start with some motivation for the problem. So let X be, for example, smooth Fano variety, which means that the anticanonical class is ample. And then the classical way to study the geometry of such varieties is by looking at the anticanonical linear system. So we can investigate the elements in this system if it is non-empty, which is always the case, for example, in dimension 3, and also in dimension 3, Shakurov has proven that such element can always be chosen to be smooth one, and hence knowing the geometry of such elements, one can say something about the geometry of the variety X. Okay, so but in higher dimensions, it could be hard to say something about this linear system, and hence one can generalize this approach and one can look at the linear system minus nkx and find and study elements in this linear system. Okay, to put it in other way, one can look at the pairs x 1 over n d, where d is from here. Okay, and then such pairs are usually called Calabi-Yau pairs, or also if Fano variety X, if we choose such a pair, then we say that a log Calabi-Yau structure is fixed. Usually people also assume that, well, this pair should have good singularities. So for example, if this pair has for example, log canonical singularities. Or, of course, one can restrict oneself to some other class of singularities like KLC or something. Okay, so in this case, this divisor 1 over nd is called an n complement. Okay, so now the goal, if we formulate it in these terms, we can say that our goal is to study all the log Calabi-Yau structures on a given Fano variety X. And to this aim, we have like many tools, many invariants that we can associate to such structures. Several of these invariants were already mentioned in this conference. So, for example, we have the alpha invariant mentioned in the talk of Hamid, or we have a delta invariant, or we have an invariant called complexity, which I will not talk about today. But invariant that I will talk is called okay. It is called regularity. Regularity. Or co-regularity. I will explain what's the difference. Okay, so now I will start to give the definition of this invariant. So now let's work in the following setting. Let us consider a pair XD, where X is arbitrary variety, say not normal, and D is a reduced divisor. So D is just the sum of the components Di. And let's assume for a moment that this pair has simple normal crossings. So simple normal crossings pair, or for short, SNC, which means that, well, X is smooth. The components Di are also smooth. They intersect in a nice way, which means that locally, analytically, the intersection of the components Di looks like as the intersection of hyperplanes in the space Cn. Okay, then we can associate to such a pair a topological invariant. So to this pair, we associate a topological space denoted by D of XD, which is called a dual complex. Dual complex of this pair. And this is a topological space, and more precisely a CW complex. So this is a CW complex, or in the terminology of Hatcher's book, this is called a delta complex, but it is not necessarily a simplicial complex, and it is defined in the following way. So let me proceed here with the definition. So roughly speaking, to each point, to each divisor Di, we associate a point. So say D1, D2, D3, and so on. And then if two components, say D1 and D2, intersect, then for each irreducible components of the intersection, we associate an edge. So if they intersect, we draw something like this. Then if we have a triple intersection, we draw a triangle, and so on. So more precisely, for each stratum of the intersection of the form Di1 and so on, Dik plus 1, we associate, so in bijection, to each irreducible component of this intersection, we associate a k-dimensional simplex or k-dimensional phase. And then if we have an inclusion of this form, then here we have k minus 1 dimensional phase, and we have a natural gluing. So here we also have to specify that we work with irreducible component of this intersection. Okay, so the gluing is defined in the natural way. And so we obtain some topological invariant associated to a simple normal crossings pair. To give an example, well, no, I would prefer in this case, so you're asking whether we can relax this assumption or what? X is not really part. Yeah, at this moment, I can say so. Yeah. And so, example, if you consider, for example, the projective space Pn, and then you take the sum of hyperplanes Di, I from 0 to n, then the dual complex of this pair will be just a simplex of dimension n-1, which is, of course, homeomorphic to the n-1 dimensional sphere. Okay, let's make the following remark. That the dimension of the dual complex is less or equal than dimension of x minus y. Why this is so? This is because of the SNC conditions. We have the restriction of the number of components they can intersect at a point. So, yeah, and also by convention, we would say that the dimension of the empty set is -1. Okay, so now we can generalize this definition, so we can somehow relax these assumptions. So, and to do this, let's work in the following setting. So now let xd be an arbitrary pair. So which means that, well, x is a normal and say projective, and d is the boundary Q divisor. The word boundary means that the coefficients are between 0 and 1. So sometimes people write like this. Okay, and then, well, let's also assume that this pair, yeah, also let's assume that kx plus d is Q Cartier. So some multiple, this divisor is Cartier. Then to associate a dual complex of this pair, we do the following. So let me write it here. We can take a log resolution that is proper birational morphism from y to x such that x is smooth. This is a log resolution, which means that y is smooth. And the exceptional locus of f, if you take the union of this exceptional locus, which we also may assume to be a divisor, with the strict transform of the divisor d, then this should have simple normal crossings. Okay. So now how do we define this notion? So we can always write the following formula: kx plus d, if we take the pullback, then it is equal to ky plus dy. So this formula is a definition of this divisor dy. In general, this divisor is just a subboundary. So in general, this is a subboundary, which means that the coefficients of this divisor belong to this set, right? But if the pair has good singularities, so essentially, if the pair has log canonical singularities, then in this case, we will have a boundary, okay, and vice versa. So actually, this can be taken as a definition of log canonical singularities. Okay, so now we're ready to define dual complex for such pairs. So probably I will write it here. Okay, so let's start from pair XD, which is log canonical Calabi-Yau pair. And here by Calabi-Yau, we mean that kx plus d is q linearly equivalent to 0. Okay, then the dual complex is defined in the following way. Dual complex of xd is defined as a dual complex of the pair y dy when we take some special part of this divisor. In a moment, I will explain what does it mean. Well, we take a log solution, like any log solution. Yeah, thank you. We take the boundary divisor dy, and then we take the sum of the components of this divisor that have coefficient 1. So in other words, one can write it like this. Okay, and then the natural question is, does this definition depend on the choice of a log resolution? And there's a theorem proven by what? What is it? This is sorry. Yeah. So, yeah. Okay. Maybe this is better. Okay. This is better. Okay. Yeah. Yeah. So to avoid confusion, let us write it like this. Some of the components which have coefficient 1. Okay. Then it was shown by de Fernay, Kohler, and Stu that this definition is correct. So it's the fact that definition is correct, which means that it does not the topological type of this dual complex does not depend on the choice of log resolution. To be more precise, it is defined uniquely up to PL, piecewise linear homeomorphism. Okay. So and for this, it is important that we deal with Calabi-Yau pairs. So this condition is important. Okay. Now we can define the regularity of Fano varieties. So let X be a Fano variety. In my talk, I will work with smooth Fano varieties. But also one can take something like KLT or LC, some good class of singularities. Then we can define the m's regularity of X in the following way. This is just the maximum of the dimension of the dual complex of the pair XD, where D is an M complement. Okay, so which means that say when D belongs to 1 over M minus MKX, and this pair has log canonical singularities. Maximum is taken among all the divisors D in such a linear system, which have good, such that this pair has good singularities. Okay, and then the singularity of X is a maximum among all the positive integers M of M's regularities of X. Okay, and then by co-regularity, we mean the, say, dual notion, which is just the dimension of x minus 1 minus regularity of x. Okay, now, well, this notion was introduced by Shakurov. And one can say that the notion of regularity measures how far a given Fano variety is from being exceptional. And now I will recall what does it mean for a Fano variety to be exceptional. So the original definition of exceptionality is as follows. So X is exceptional if for any log canonical complement D, we have that the pair XD is actually KLT. Well, to be KLT, sorry? Yeah, if log canonical is a part of the definition of the complement, it is automatically, yeah, but I just want to stress that we take log canonical divisors. Yeah, KLT means that here we have this condition for the boundary divisor dy between 0 and 1 is, yeah. So in other words, to be exceptional is the same as to have regularity -1, or that to have regularity equal to the dimension of x, right? So let me make the following remark. Regularity of x belongs to the set -1, 0, dimension of x -1, and co-regularity belongs to the set 0, 1, dimension of x. So being exceptional means that we are here, okay? And hence the regularity measures how far we are from being exceptional. So perhaps for this reason, co-regularity should be better called exceptionality. But now I guess the co-regularity is a standard. Now it is a standard term. So let me give a couple of examples. So let's start with the most simple example of a toric Fano variety. So if X is toric, then we can take as a boundary, we can take the sum of all torus invariant divisors, torus invariant prime divisors. And then it's well known that first of all, we have AX plus D equivalent to 0. And then this pair has good singularities. It is log canonical. Moreover, up to taking the toric resolution, we can assume that this pair is SNC, say log smooth. And since there is always a torus invariant point, so we have a stratum of the dual complex of dimension 0, and thus the co-regularity in this case is equal to 0. Okay, so this is simple. So we see that toric varieties live here. Okay, now one more example or class of examples. Well, we can consider delta surfaces. So X is a smooth delta surface, which is a Fano variety of dimension 2. And we can ask what about co-regularity of those? So, as was mentioned in the previous talk, over an algebraically closed field, we have a very nice classification, and the main invariant is the degree of the anti-canonical class. So let me denote it by D. And well, of course, we know that if D is at least 6, then X is toric. So the corregularity is 0. So let's investigate the following cases. And it turns out that if D is between 2 and 5, then corregularity of X is always 0. And the reason for this is very simple. Well, it is a nice exercise in birational geometry to find an element D in minus kx such that D is isomorphic to nodal curve, right? Actually, if the degree is at least 2, there is always such a curve. And then let's compute the dual complex of such a pair. So X and D. Okay. Well, this curve has one singular point, so we blow it up, and we get log resolution. So Y to X. I will write it like this. And now let's compute the log pullback in this sense. Well, Y dy. First of all, in dy, we have the strict transform of our curve, and we also have the exceptional divisor E. So the picture is somehow like this. We have nodal curve, and then we blow it up. We get exceptional divisor E, and then the strict transform. So they intersect in 2 points, and the dual complex looks like this, right? So its dimension is 1, hence regularity is 0. Okay. All right. But this is no longer the case for degree 1 del beta surface. If the degree is 1, we can not always find such a curve, such a nice curve in the anti-canonical linear system. So let me explain. In this case, X can always be embedded in the weighted projective space with the following weights, and we can write down the equation of X in this form, like F6 y plus F4 xy z plus z to the 3rd power plus w. That's like this. Or maybe let me give an example of a surface such that it does not have nodal curves. So I erase it. Okay. And I can write something like this. Yeah. So generically, so a general del beta surface of degree 1, it has 12 nodal curves, but this one, it has 6 cuspidal curves. Okay, and hence, well, the pair is not log canonical, and one can check that the other curves in the anti-canonical linear system are non-singular, right? And so hence the first regularity of X is equal to 0. Okay, and actually for this example, one can show that the regularity of X is equal to 0 without the subscript 1. Okay. And so the answer in this case is as follows. Generically, for a general one, the regularity is equal to 1. But for special, the regularity is equal to 0. And one can specify what do I mean by special here. We have one-dimensional moduli of such surfaces. And for three-dimensional closed subset, which corresponds to this case, we have co-regularity 1, and for general, we have co-regularity 0. Okay, so this is fairly simple. Yeah, this is a good question, and it turns out that it is not. It is not upper nor lower semi-continuous. And I will talk about this a bit later. There are some results about semi-continuity for such pairs, but if we fix the polarization, if the polarization is not fixed, then we don't know. Okay, and now let me explain how to obtain this implication. Well, I explained that in the anti-canonical linear system, we cannot find a good element. But, well, according to the definition, we have to care about all the linear systems, like minus MKX, which looks difficult, but there is the following theorem. Well, now I have to consult the list of the authors, which is quite long. Which was proven by, yeah, sure, because otherwise the list would be quite short. But I mean, theorem proven by Figueroa, Filipazzi, Moraga, Peng, and also very recently, a couple of weeks ago, it was reproved. So there was a different proof by the following group of authors. Bloom. Liu and Wong. So actually, the list of the authors is longer than the theorem, but well, if X is so canonical Fano of co-regularity 0, then we can find either a 1 complement or a 2 complement, such that the co-regularity is evaluated by this divisor. Sorry, second. Yeah. Perfect. Yeah. Maybe I can. Yeah, that's true. Like 2 lines. So then either correct 1 of X or correct 2 of X is equal to 0. Well, of course, yeah. If if the co-regularity is attained, then if you take multiples, then the same value is attained also for the multiples. But up to, yes, but about monotonicity, it is not known. So for multiples, you can take, but so in general, not much properties of this function is known. So as we will see, it can behave in a complicated way. Okay, but the good news is that to check the regularity, to check whether the given variety has co-regularity 0, so to this aim, you have to check only the linear system minus k and minus 2k. You don't have to go further. Sorry. Say again. Yeah, there are several papers, but as far as I know, the statement about co-regularity is, at least it is like written in an explicit form in this paper. No, I may be wrong, but yeah, there are several papers with different groups of authors. Sorry? Question? No, I don't want. So once again, if X is a log canonical Fano of co-regularity 0, then this co-regularity is attained either on or for one complement or for two complements. Yeah, that's true. To prove it. Yeah, that's true. Okay, and now we have computed the co-regularity of delta surfaces, which is quite easy modulo this theorem. Now the problem proposed by Hakin Maraga is to compute this function for some known families of examples, and so compute the function for example, smooth or mildly singular threefolds. Well, and in the remaining time, I hope to explain how we can do this. So we have the well-known classification, like 105 families. The classification of Iskovsky, Khmuri, and Mukai. So now let me explain that. First of all, what was the expectation? Looking at the example of delta beta surfaces, we can expect that for most smooth Fano varieties, we have co-regularity 0. And in some sense, this is indeed the case, as we will see. And now, let me start with some easy cases. This is exceptional or non-exceptional. Exceptional means that we don't have strictly log canonical singularities at all. We don't have strictly log canonical complements at all. In particular, this implies that the minus kx is empty. Yeah. Well, formally speaking, it's either empty or all the members have very bad singularities, right? For smooth threefolds, it's not possible. You're right. Yeah. It may be possible. Yeah. Okay. So easy cases. Well, according to the classification, there are 18 toric Fano varieties. So for 18 cases, we're safe. We have co-regularity 0. Let's consider some simple non-toric examples. So let's start with the Fano varieties of index at least 2, and recall that the index of x is a number by which we can divide minus kx in the Picard group. So here h is some ample divisor. And so, well, for example, if I is equal to 3, then we have a quadric. And well, we can take 3 hyperplane sections. So quadric lives in P4. We have 3 hyperplane sections. The first section gives you 2-dimensional quadric, and the second section cuts a conic on it, and the third one cuts another one if we take these guys to be general. So we have a 0-dimensional stratum for the intersection, and hence co-regularity is 0. So this is very easy. Well, if the index is equal to 2, the approach is similar. So here we have a Fano variety X. We can take 2 hyperplane sections, but now we assume that they are quite special. So in which toric case? Well, maybe I mean the number of divisors can be different, right? So yeah, sure. I have said it somewhere before. Yeah. Yeah. Locally, this looks similar. Yeah. Okay, so here we cannot take more than 2 divisors in -k, so we take them to be special. So each of them is a Del-Pezzo surface. For general, it is smooth. And then we take them in such a way that they intersect in some nice curve, for example, in a nodal curve. And then a simple, so this is D1, and this is D2, and then a simple calculation. So you blow up this point, and then you compute the dot complex, and it turns out that, well, upstairs, so on a local resolution, it will have a 0-dimensional stratum. Let me also make the following remark, that you don't have to take a local resolution to compute dual complex. So remark. So it is enough to take a so-called DLT modification instead of local resolution. So recall that a DLT modification is such a morphism that well, I would say it like this: a pair is DLT if there exists such a morphism such that in dy in dy all the exceptional divisors come with coefficient less than 1, and dy is a boundary. Okay, so this is the definition of DLT, and DLT modification is somehow more minimalistic than local resolution, so it is more convenient for computations. Okay, and now here we dealt with the case of index 2. Know that, well, in the case of degree 1, so where h cubed is equal to 1, one has to be careful, and one can prove that the co-regularity is 0 for general. For general X, for the reasons similar that I explained to the one that I explained above for Del-Pezzo surface of degree 1. Okay, well, now let us exclude some other simple case. This is the case of Picard rank at least 2. So in this case, Fano variety, in many cases with this condition, a Fano variety X is obtained as a blow up of some other variety. Let me denote it by Z. So this is blow up. X is a blow up of some curves or points. So blow up of some subscheme W on Z. And let me illustrate that such cases are also fairly simple. As an example, we can take a variety from Hamid's talk. So very nice one. You have P3 as Z, and then you blow up a line and a rational cubic curve. So this is L1, and this is C1, and this is C2. Okay, so in this case, W is the union of C1 and C2. And now we just find some nice boundary on P3, boundary D prime on P3, such that it contains these centers of the blow up. So we can take, for example, a quadric that contains C2 and a plane that contains C1, and also we can take another plane in general position. So we take these three divisors, we take their sum. This is the boundary on P3, and then we take the log pullback to X, which actually just the strict transforms of these divisors, and they have a zero-dimensional stratum. Hence, co-regularity is also zero in such cases. Well, to be precise, in the case of Picard rank at least 2, there are also 12 families which cannot be obtained like this. So yeah. And there are 12 families of varieties that cannot be obtained in this way. But for them, so for example, we can take a divisor of by degree 1, 1 sitting inside P2 cross P2, right? See, so it's neither toric nor have birational contractions. But in this case, also it is not hard to construct boundaries that evaluate co-regularity 0. Well, but well, yeah. In this case, I also, let's say that in this case, I assume that the Picard rank is 1. Yeah, to be more precise, okay, these are the most simple examples, but sometimes you need a more careful analysis of the geometry of your variety to construct such pairs. You want some good divisors, like which are non-singular or something like this. Okay, and now let's go to the interesting cases. So interesting cases are as follows. If the Picard rank is 1 and the index is 1, then such Fano threefolds called Fano threefolds of the main series. And this is the most interesting one because, well, because of the index 1 condition, we can take only one hyperplane section. So, yeah, what I want to say that in all the previous cases, so let me make this remark. In all the previous cases, co-regularity was equal to the co-regularity to the first co-regularity of X, and this phenomenon is somehow similar to the computation of the alpha invariant of some Fano varieties. For example, for Fano fourfold, if you compute the alpha invariant, then it is enough to look for the linear system of minus kx. Okay, so yeah, going back to the main series, if the genus is large enough, then everything is fine. So let me recall what a genus is. So it can be defined like this. So this is just the dimension of -2, or also we can say that this is 2G minus 2. Okay, so if the genus is big enough, so if it at least 6, then well, for general X, regularity is 0, and to show this, one can use the method of the double projection of Iskovskих. So essentially, it gives some very nice birational transformation of the given Fano variety. So, for example, let me write down some diagram. For the case G equal to 8, we have something like this. We have X. We blow up a line. So this is a blow up line of a line on X. Then we have some small modification. We have a flop, which leads us to some other variety V prime, and then we're going. We blow something down to a curve, and we are on P3. So this is a birational map to P3. Here, this map is a blow up of some curve of degree 7 genus 3, and so we can take some. Let me. Yes, you're right. Yeah. Thank you. Thanks. Okay. So what we can do here is the following thing. We take some boundary on P3. For example, we know that this curve lies on some cubic surface S, which we take to be the first component. Then we can take some other component such that co-regularity of this pair will be 0, and then we pull it back here, make a birational transform, and push it down to X. And then if you do this carefully, you will see that the co-regularity of this pair, of the obtained pair, is also 0. So why do we need generality assumption? Because we know that this surface is non-singular, or it has nice singularities only for general such X. And also, this surface is exceptional for this arrow. Yeah, that's true. And then the second component becomes the only component of the boundary here. Yeah, that's true. Okay, now the most interesting cases. Most interesting cases are when the genus is at most 5. So, well, the previous computation might give you the feeling that, well, actually co-regularity is always equal to 0, but a kind of surprise is that this is not the case. So for general X, for general X of the main series with genus at most 4, the co-regularity is not equal to 0. So it is at least 1. And now in the remaining few minutes, right, I have to explain why, at least very briefly, I will try to explain why this is the case. So consider the case of a quartic in P4. Okay, so why the co-regularity is not equal to 0? According to the theorem, I have to look either at minus k or minus 2k, and let's start with minus k. So minus k is simply this system of hyperplane sections. So I take the hyperplane section, then it's easy to check that it's normal. And let's consider this situation locally. at some point P inside X, this hyperplane section can be singular only if singular at P only if it coincides with a tangent hyperplane at P. So I can assume that this is a tangent at P. And now we need some local analysis of singularities. So if this pair is purely log terminal, we have that the dual complex is just 1 point, so it's not interesting. But it is somehow singular, right? So yeah, I assume that this pair is strictly log canonical. So by inversion of adjunction, D is strictly log canonical, and then we need to analyze how many conditions that this imposes on the equation of X. So if X is given by some equation, we take a look at this equation locally near P. We intersect it with D, and we have an equation of a surface in C3. So F restricted to the tangent space, which is D. So it gives us equation of our surface D, which we may assume to belong to C3. And now the question is, how many conditions do we impose to have a strictly LC singularity? Well, this can be analyzed. You write locally the equation, you look at the conditions, apply some singularity theory, and it turns out that the codimension of this condition is at least 4. For a fixed point in the space of all quartic threefolds that pass through this point. And hence, if we vary this condition for all points of X is 3-dimensional, right? Hence, we see that for general X, there are no hyperplane sections which give you a strictly log canonical singularity, and hence this cannot happen. So D is KLT, hence this pair is PLT, and the dual complex is just 1 point. And the analysis for the second case, so where D is from for a general, for a general X, we cannot find. For some special, we can find such hyperplane section that will be a cones, look like a cone locally, so it will have log canonical. Yes. So, but for general, we have at least one. So I have a regularity at least 1. So co-regularity at most 1. Yeah. For special, it will at most 1. If I have a cone, The question, if I have a cone, I have first this component, and then I blow it up, and I get 1 more component. So regularity is 1. Regularity 1, co-regularity 1. So I need something more to have a maximal complex. But in this case, the analysis is more complicated because you have to consider all the quadrics, which are singular at some point, and then you write down local equations, and it becomes so it is case-by-case analysis of types of singularities which are worse than log canonical, but essentially we are interested in the log canonical thresholds of all the quadrics that pass through the given singular points. And it turns out that for general X, for all the quadrics, we have that this pair is KLT. And so nothing interesting here. And in the other cases, similar considerations apply, although they become more complicated when the genus gets larger. So for the larger, for the intersection of a quadric and a cubic, this case-by-case analysis, it took many pages. So the singularities that are there, that they are quite nasty, but one can formulate the following theorem. Which says that, well, as I explained, if if X is a smooth Fano threefold, so if the Picard rank, if the Picard rank is at least 2, then coregularity is always 0 in 2 families, in 2 cases, for general element, in all the rest of the cases for all. Then if Picard rank 1 index at least 2, then also coregularity is equal to 0 in one case for a general member of the family. Finally, if rank 1 index 1, then for genus at least 6, then coregularity is 0 for general, because we need some generative condition to draw such diagrams as there. And finally, where G is at most 4, then coregularity is at least 1 again for general. And there is only one case that we still don't know about. It is the intersection of 3 quadrics, where this case-by-case local analysis of singularities becomes really complicated, takes like many pages, but we hope that we can deal with it finally, and we are expecting that we have also coregularity at most 1 here, and sorry, at least 1 here. Yeah, and let me also, so finally, let me say that this theorem can be restated in terms of the degree, which could be possible, which could give an idea for generalization. So corollary, so if the anti-canonical degree is at least 10, then we have coregularity 0 for general. And if the anti-canonical degree is at least 24, then we have coregularity 0 for any. So maybe this type of statement is possible to generalize to higher dimensions, because after all, in higher dimensions, we don't have classification, and maybe some local considerations can help us to prove this theorem. So this is it, I guess. Time to stop. Thank you for your attention.
Thank you for the nice talk. Are there any questions or comments?
For general is what? Yeah. In some cases, I think it is possible to prove that really for special you have a different value, but I mean it should be not complicated, but we were not very interested about it. Yeah. So. Yeah, sure. Of course, these bounds are not optimal. Maybe these bounds are they are really different. So yeah, and it will be interesting to understand which bounds do you need in any dimension? Will it be like n to the power n or something like this? So in this case, I mean, yeah. For general, I have co-regularity at least one for quartics. Not zero. Co-regularity not zero. Yeah. For special ones, it can jump. So regularity can jump and co-regularity can become zero. So again, you need to write down some explicit equations. Yes, as these two examples showed, it could jump in both directions. As the case of Telpetsa degree 1 shows, the regularity can jump, can become lower on a closed subset, and this example shows that it can become larger, bigger. Yes, in principle, it is possible. Yeah, but again, it is hard to prove that you have co-regularity larger than one because you have to investigate higher linear systems. Like, yeah, there are such theorems. So you can you should always look for the bounded complements. To get some singular members, you should look for the bounded complements when the bound depends on co-regularity. Yes, because it would take looking up to -6 kx, and here you really need a different technique because the analysis of singularities becomes complicated at each step, more complicated at each step. Yeah, it is somehow. Yeah, it is somehow related with birational rigidity. So here we played at the fact that for higher genus we have some links of this form, but if your variety is rigid, you don't have such things, so you have to do something else. Yeah, sure. Which are singular along some centers. Yeah, this is very similar, actually. Yeah. Well, there is a theorem by the second groups of authors of this big theorem that if you fix the polarization, so if you consider a family of the varieties xd, so then this function becomes upper semi-continuous, but with fixed d. And the problem is that if you vary this boundary, the boundary divisor. So if you vary the boundary divisor, so if it was log canonical, then the limit may not be log canonical. So that there's, yeah. Yes. So you have a family of your variety plus the divisor. Yeah, and then the function co-regularity for such pairs is upper semi-continuous. This is what they prove. Yeah. About what? Sorry. Under field extension. Well, I don't know. This is a good question, but I don't know. So, well, essentially, it seems that co-regularity can become only can go down, right, under field extension. So maybe one can prove this, but what else can be said? I don't know. Yeah. Sure. Actually, before we put the results, so we saw that you have a long delta of regularity zero, then one of the complex. And this is even stronger than the result. So it works for like Fano type or Calabiao. Yeah, but local ABL, yeah. Of course, this more general, yeah. But our goal was to compute it at least in some explicit examples. So maybe for terminal Fano threefolds, it would be more interesting. I mean, because you don't have classification, you have to work out some new technique. But yeah. One and two is just the fact that it's more complex. Yeah, I understand this, but I mean. So for me, it would be nice to have such a statements generalized in higher dimension, because really there should be a bound, lower bound for the anti-canonical degree. So essentially, this is very similar to the method of Shakurov of creating log canonical centers. So if you have large anti-canonical degree, then you can create some centers, but explicit bound. So it would be good to know one. Okay.
Are there further questions? If not, let's thank Konstantin again.
Thank you.